I hate when aluminum foil resists being torn correctly. You know, speaking of aluminum and resistance, I know what I should do for my physics project. In my physics experiment, I'll be solving for the resistivity of aluminum. Resistance equals resistivity times length over area. Well, length is pretty easy to solve for, and that will be what we're changing throughout this experiment, such as lengths of aluminum from this size to this size, as in from 2 feet, 1 foot, or 6 inches, which, don't worry, we'll convert to standard units later on. The other part is we need cross-sectional area, which would multiply length times width. Well, this length is 3.8 centimeters, and this width is 0.3 centimeters. So we'll multiply and convert that to meters later on. But the tricky part is solving for resistance. By doing this in my experiment, I will have a battery, a wire, and that wire will connect at the end to these various pieces of aluminum. At the other end of the piece of aluminum, we will connect one end of a multimeter and the other end back to the battery. On that multimeter, we will get a reading of the current. Because the voltage will be consistent throughout the experiment, we can easily solve for V equals IR and solve for the resistance throughout each length of aluminum. As you can see, the battery, wire, aluminum, and multimeter are all in a series. We will repeat this setup for all 3 different lengths of aluminum. Another important part of the procedure is accurately measuring the voltage of the battery using the multimeter. After recording all the data, we can determine that for the 2 feet, 1 feet, and half a foot, which have now been converted into meters, these were the currents going through each of the pieces of aluminum. Now we can take this data and convert it into the V equals IR equation. Well, V is going to be constant given it was the same battery source every time. So V equals I from the 2 feet or 0.61 meter, R, so R equals 0.059. Well, resistance equals resistivity times length over area. And as we already determined, area equals length times width, which would be 0.038 times 0.003, which equals 1.14 times 10 to the negative 4th meter squared. Well, we can solve for resistivity, and rather than just solving for resistivity for each of these 3 units, it'd be best to use it and look at it in the form of a graph. So, graphs are obviously rise over run. So resistance times area over length, or y-axis over x-axis. So we come down here, and we still have the length the same, but now we're multiplying the resistance that we already solved for times the area, which will be constant for each one, and we get these values. As previously mentioned, to find the slope, we take the rise over run, or y-axis over x-axis. In this case, our y-axis is ohms meter squared, which is from resistance times area. Our x-axis is length in meters. Well, ohm meters squared over meters yields ohm meters, which is the unit for resistivity. That's how we get our slope being resistivity. Another trend to be noted is that as the length of the aluminum pieces increases, the overall resistance of that piece of aluminum increases as well, which is a true trend. As you have more of a material, the resistance will increase. Idealistically, our slope should be exactly the resistivity of aluminum, and our y-intercept to be 0. However, this is not the case. Percent error equals the estimated value minus actual value over actual value. So we can take our estimated value of the graph, which would be 1.868 times 10 to the negative 6 ohm meters, minus an accepted value per hypertextbook.com, which is 2.65 times 10 to the negative 8th ohm meters for the resistivity of aluminum. While doing this calculation, we get our percent error to be 6,949%. With a percent error that large, it's pretty fair to say my experiment was kind of a failure. However, there are no failures in physics. Part of my experiment probably had error due to my experimental design. As you probably noticed earlier on when I was recording one of my trials, by holding the multimeter to the series led to a lot of variation in the numbers. This is because it's hard for you to keep your hand exactly steady to record the data perfectly. If I could develop some sort of way to keep that constant every time for the different lengths of aluminum, that would have greatly reduced error. In addition, I didn't have all the tools available to me to really make a proper experiment. See, I didn't have clips to keep the series all together, so I had to rely on masking tape to hold a lot of my experiment together. In addition, the largest battery I could find is just this 1.5 volt battery. If I could have had a 9 volt battery, the increase in voltage probably would have overcame some of the resistance, whether from the wire or from just like, say, 2 feet of aluminum. Regardless of the trials and tribulations of having to have a science experiment at home, we can still determine that an increased length or an increased in amount of material that a current has to travel through will increase resistance. That's apparent by the trend in the graph. And at least we can tell that from formulas, resistance times area over length will yield resistivity. However, my calculations are just a little off.